And now I'm going to explain the evaluation section of the mark scheme for the internal assessment. The evaluation is actually comprises of two parts. You have a conclusion section and an evaluation part. For the conclusion, you need to do the following. You need a conclusion which is described and justified and relevant to the research question and fully supported by the data presented. For this, you must go back to your original research question and you must answer it simply. You also need to use the data to justify that answer. I'm going to give you an example. Say the research question was, what is the specific heat capacity of copper? Okay, so it's not really an investigation, it's more a very close practical, but it's a good example. Okay, so what is the specific heat capacity of copper? By entirely relevant to research question, our answer must be the value of the specific heat capacity. Now let's say that you worked out with your graph and your maximum and minimum gradients, you worked out a value of 400 joules per kilogram per Kelvin. Okay, and your maximum and minimum gradients gave you a value of 30 either way. Okay, so that is your conclusion. My value of the specific heat capacity for copper is 400 plus or minus 30. So what do we mean by a conclusion that is described and justified through relevant comparison to the accepted scientific context? Well, what is the real value of the specific heat capacity? It would be expected that you research and you find the actual value. The actual value of the specific heat capacity of copper is 386, more or less. Now, your value is similar, but you can say more than that. Your value is 400 plus or minus 30. If you take the minimum possible value for the specific heat capacity, it would be 370. If we look at the range 370 to 400, the actual value falls well within that. So your conclusion would be, your full conclusion would be that your specific heat capacity is 400 plus or minus 30 in comparison to the real value 386. My range includes that actual value, so therefore my experiment was successful. So this is what we mean by a relevant comparison, taking the theory and comparing it to what you actually find. I've outlined that in the pupil section, the pupil guide section, that you've stated your conclusion using the results, that you've made a comparison with the actual result. You mean you've done some research and you found out the answer that you were supposed to get, and you use the uncertainties to state the validity of your conclusion. You see if the actual value falls within your plus or minus range. Now we're going to look at the evaluation side to this section. The first thing you must do is state the strengths and weaknesses of the investigation, the limitations of the data and sources of error. And you must discuss these and provide evidence of a clear understanding of the methodological issues in conclusion. Well, let's try and take this apart. The first thing you should do is comment on the strengths of your investigation. If you found that your value coincided with the real thing, then it's safe to say that you did something right. Okay, so what parts of your experiment worked well? Obviously, it's harder to say this if your value is completely different from the real thing. So you do have to be a little bit careful with this. The next thing to do is to state all the limitations of data. So where is it possible to make mistakes? There are some which are classic sources of error. For example, in timing errors, there's reaction time. Reaction time. Are there parallax errors? If you're doing experiments with heat, think of all the possible places where you're getting heat, or rather thermal energy loss. Is the electric heater you're using completely heating the object that you're looking at, or is the heat going elsewhere? Have you used correct insulation? It is in fact far better to think about these things while you're doing the experiment and while it's still all fresh in your mind. So when you're doing your practical work, it's worth making some notes as you go along. Now those are your limitations and your sources of error. To be more specific, a limitation would be something that you really can't help. There's nothing you can do to try and avoid it. So heat, energy loss is lack of enthusiasm. Well, not necessarily lack of insulation, but lack of complete insulation would be a limitation. You might be able to wrap the object that you're warming, try and keep it as warm as possible. There's always going to be some heat loss that you can't avoid. That's just a simple law of physics. But an error would be if you insulate it badly. A reaction time is another limitation, but having a really odd result, which was obviously the source of an error, or that would be mistakes. That would be more errors. Sources of errors listed. Okay, you don't have to differentiate these two, but I will definitely try and find some examples of each. Now, if you could then go on and explain what the consequences of each would be, then this would show, if you go back to the original mark scheme, this would show clear understanding of the methodological issues involved in establishing the conclusion. So a reaction time, for example, would produce a systematic error, which you can see and read on your graph. It's the intercept. The same with a parallax error if it's systematic. Insulation might cause a completely different value in your gradient, for example, or more likely, once again, it would be a systematic error which will come across in your intercepts. So it's very important that you show that your limitations or sources of error have consequences on a graph and that you can explain why. Okay, so what do we do to show or to try and compensate for these mistakes? Well, you can give realistic improvements for those limitations, and by realistic that means things that you can actually do. So for example, if you're doing reaction time and you would like to reduce the reaction time error, then you could maybe come up with other ways of measuring time. For example, you can film and then use the timing reading on the film itself to measure time. You can use data logging and sensors, which are more sensitive. Sensors. Okay. Parallax errors, you can carefully find a point of reference, or film, again, as a way of reducing that parallax error. With heat and energy loss, again, remembering to insulate always. And if you didn't insulate enough, where could you insulate more? Think about maybe design features. Design an experiment or even a piece of equipment that would help you improve the error that you pointed out before. The idea is that for each and every one of these limitations and sources of errors, not only have you explained what the consequences are, but you've actually followed through and come up with and designed some way of reducing their effect. Now, the extension of investigation, that's something you would add, but more for your real internal assessment when you're investigating. In what way could you pursue your research question further. In fact, this is the whole premise behind scientific investigation. You have a research question which fuels a hypothesis, which you do an experiment to prove or disprove, and then what that does is develop a research question again. So it's kind of a cycle continuously. So if you are going to provide an extension to your investigation, it should be somewhere along the lines of where you're going in the first place. But we'll talk about this when we actually start looking at experimental work in investigative contexts.